to examine the distribution of anthropometric measurement of the two data sets we are going to evaluate our models on. So the task is called a human shape estimation. So in the current setting, there are two data sets that most people use for this task. The first one is called SSP-3D, and the latest one is called HBW. So we would like to examine how these models, how these pictures, how these people in these two data sets look like. What's their BMI, what's their body shape. And the reason for this is that if we trained our model on the training data set that does not contain extreme BMI, that does not contain people with extreme BMI values, for example 3DPW, then our model may perform poorly on these two data sets. So first, we would like to examine the BMI distribution of these two data sets. Not only BMI, but also the four body measurement, height, and chest circumference, waist circumference, and hips circumference. Okay, so the whole pipeline is that for the first data set, which is HBW provides these data set provide the ground truth SMPL-X vertices. So we will read these SMPL-X vertices and feed these vertices directly into the virtual measurement library provided by the author of the of Sharpie. Sharpie is the paper that the author of Sharpie also provides HBW at the same time when their paper was published. So we use this virtual measurement to feed in the SMPL-X vertices, which is every person is represented by 10,475 vertices. So these vertices will constitute the body meshes, and these body meshes can be used to predict the so-called anthropometric measurement, which is more briefly or more shortly just the height and the three circumferences. So we can see that the pink one is the frequency or the occurrences of female in height, and the blue one represent the male data. And we can see that most of this data spread a wide range of height and chest and waist. But if we only look at one specific measurement, it is not guaranteed to faithfully represent the body shape of the person. So we calculated the BMI by using the predicted height, predicted mass, and divided by the distribution by the predicted height by the squares of the predicted height. So we can see that the BMI of this validation data set range around from 20 to 32. Okay, so if we find what is the normal BMI of adult, okay, so the normal BMI is between like 19 to 25. So in this data set, we have from around 20 to 32, and then we have the normal BMI from 19 to 25. So we do have some data that is beyond the normal BMI range. But there's a little bit caveat here, is that the predicted mass is calculated by multiplying the volume that is surrounded by these meshes and multiply the volume by a constant density, which is the author claimed in the original paper is a constant, is like 900 kilogram per meter square, per meter per meter cubic. So these assume that everyone has a constant body density, but we know that it is not the case. And this caveat can be represented very clearly in the second data set. But before that, we just compare the data set that for most one of the popular data set for training is called 3D-PW. So we can see that this legend is misleading. So the blue one is the distribution of the four body measurement, height, and the 3 circumference. So we can see that the blue one is the measurement for 3D-PW, and the red one is the measurement for our HBW. We do see that most of the cases in the 3D-PW data set, they invited a model that with more normal body measurement. So the distribution really concentrated on certain body measurement. So if we trained our model on 3D-PW and we would like to inference our model on HBW, so you have, of course, the model inherently didn't see data that has a so wide range of body measurement or in terms of BMI. Okay, and later in the next video we will also examine the BMI distribution of our training data set, the 3D-PW and COCO, etc. But in this video, we just want to examine the two data set versus HBW and the distribution of BMI, primarily BMI on our evaluation data set. And the second data set, which is the most models were evaluated on this data set, is called SSP-3D, which is sport, shape, and pose 3D. And let's see. So for SSP-3D, we can see that they also have a wider range of BMI, ranging from almost 18 to 60. that's a really wide range and even wider than the distribution of HBW. Okay, so we know this characteristic of these two data sets, but we want to know whether the body measurement is accurate. Okay, so for SSP-3D, they provide the SMPL parameters. Okay, they do not provide SMPL-X vertices. So what did we process these SMPL parameters is that we use the so-called Bomoto. Bomoto is a GitHub project that you can transfer. Of course, is provided by Max Planck Institute for Intelligent System, and you can use Bomoto to transfer between parameters of two representation system. So the simplest case is just transfer. So we just used the simplest one to transfer the SMPL parameters into SMPL-X parameters. And having these SMPL-X parameters, we can use these SMPL-X parameters to generate the SMPL-X vertices. So from these SMPL-X vertices, we just feed again into the Shapley virtual measurement and to get the so-called predicted anthropometric measurement. Okay, so this approach is quite lengthy and time-consuming, but I'm not sure whether you call time-consuming. It's just the first step. We need to build this kind of pipeline. But of course, there are another approach that provided like by this author, David Boja. I'm not sure. They do provide some model and to directly predict the body measurement from SMPL parameters. So the mechanism is similar. Just you feed in the SMPL parameters, and the model will use these SMPL parameters to build the SMPL model. And the SMPL model do have their 6,890 vertices, and use these vertices to generate the body measurement. So we tried both, and we can see that the distribution is kind of similar, right? Although you can see that some data do vary under these two body measurements. So on the left is the body measurement we use by the Shapley virtual measurement, and on the right, on left is for virtual measurement, and right is used directly through a kind of third-party self-developed measurement. So we can see that the overall distribution is almost the same, and if we overlay these two, we can see that the yellow one is the one we got from the third party from this one. Okay, SMPL anthropometry, and the blue one is from the Shapley, which is the author of HBW. So we can see that the distribution is almost the same, but they do have some minute differences in terms of their their distribution. Okay, but we also would like to ask, the virtual measurement here we use is specifically provided by the author of SHBW, which is the data distributor of HBW, whether this virtual measurement is accurate also on the SSP-3D. So we just SSP-3D, they do have 62 models, 21 female and 41 males, and we just examined the SSP-3D measurement, and we picked the data that have an extreme BMI like 40 or even 61, and also we picked some data that have a relatively small BMI, and we can see that they do align with the picture depicted in the data set. Okay, although I really don't think that this man have a BMI of 19, but it's just visually it may like 21, something like that. But really, I'm really not so sensitive to the BMI with the images in terms of BMI. So, but roughly the images, the people in the image do have a body shape that is correspond to their BMI. Okay. For example, we can see that for bodybuilding, they tend to have a smaller BMI here. Okay. And for diver, they also have a smaller BMI. And so for Olympic weightlifting, they do have a higher BMI here. So we can see that for a very simple example is for the same BMI, as we mentioned that the kilogram, the mass or the body weight was calculated based on the assumption that everyone has a constant density of your body body composition. But in this case, we can see that somebody is more fit and somebody may be more corpulent in terms of density. And for weightlifting, maybe this person has more muscular, although they are kind of in terms more sturdy, but it's not fat. They do tend to have a more stronger muscle tissues, and so their density may be larger. So, and also like the data point of sumo, Japanese athletes, they maybe have a mixed of fat and muscle. So I'm not sure whether assuming everyone has the same body density is the correct assumption. But of course, in the original paper in SHBW, they do not compare directly on the body mass. Just to be concise, the body mass is not the metrics to be examined, to be compared. The only metrics is the four measurement related to height and the three circumferences, and also of course the vertex to vertex vertex error. Okay, so of course what I want to say is that the BMI distribution, we said that we want to examine the body shape distribution because the data is so many, and we would like to have a really a brief look at the data set we are going to be evaluated. We are going to evaluate our model on. So this BMI graph is just give you an overarching view of the body shape distribution of our data set, not really the exact body shape distribution, as the assumption of everyone having the same body density is of course erroneous. Okay, so in the next video we will look at the 4 data set we are going to train our diffusion model on, which is COCO, MDI, MD2, and of course 3D PW. And after examining the anthropometric distribution of these 4 training data set, we are going to discuss why we would like to adopt the synthetic data set training process introduced by the author, which was a PhD student at Cambridge, Straps. Of course, why he adopted this kind of approach. And finally, just a reminder that SSP-3D, as the name suggests, most of the people in this data set do wear a very tight clothing. So when using something like silhouette as your proxy representation, it do have a better performance. But for the latest HBW dataset, a lot of the people here in the image wear a relatively loose clothes, so using silhouette may not be a good representation of the person in the image. Okay.